All right, this is the second hour of Physics 1C for May 11th, and the next thing we're going to talk about is displacement current. And I think somewhere over here I have, let's draw some stuff first, and then I'll pull those diagrams in. Okay. So, So we've been talking about electricity and magnetism this whole semester, and probably before you came into this class, you had heard of Maxwell. So Maxwell, his full name is James Clerk Maxwell. He's a Scottish physicist, I believe. So he's from United Kingdom, like northern part. And he was someone that was working in the fields of, I want to say he was studying like fluid flow. I can't remember for sure, but I'm pretty sure he was studying like fluid flow and started to realize that some of the equations that were being used to describe the way that fluids flow could also be used to help describe electricity and magnetism, and so he switched his focus over to that. And he was like kind of like a pure theoretical physicist who worked mostly on trying to come up with descriptions of how magnetic fields were produced, electric fields were produced, stuff like that. And one of the things that he did was to look at Ampere'S law. So just to remind you what Ampere'S law is, it's the equation that you get when you do the line integral of B dot dl. And what we found when we discussed this is the answer is mu naught multiplied by the current that is enclosed by path. And normally what that means is that if I have some current carrying wire like this, and around this wire I draw some type of a path, let's use a circle. Around this wire, if I draw some type of a path, like let's say like this, let's make it a different color so it stands out. That if I have this being my current enclosed, going this way, then if I do a path integral around that current, like let's say it would be the other way, right? Okay, so we're going to go around this way and then back down this way. Think of this as being the front right here. That basically, when you're doing this line integral, you have a path, so here's your path, and you do the line integral around that path. But the idea is that that path has a boundary, and that boundary can describe a surface. And the surface that it describes in this case would be this surface right here. And then you just say, okay, how much current actually passes through that surface? And in this case, it's just the current I enclosed. That's what it's defined as. But what Maxwell realized is that you don't have to just use this surface. You can use any surface that's bounded by this path, and you can still make Ampere's law work. But there's problems that occur in certain situations, and so he had to come up with a way to deal with those problems. So this is the problem that he figured out. Suppose that I have a system where I have a wire that is connected to a battery. So here's my battery down here. And we include a switch. We include a resistor, R, and we include a capacitor. So we have some EMF, some resistance, some capacitance right here. Okay. So we know that if you close the switch here, so we close at t equal to 0, then what's going to happen is that there's going to be charges that start to develop on this capacitor plate here. And so let's define the charge at a moment in time to be Q. So Q is going to represent just the charge, like instantaneous charge or charge at a moment in time. That's obviously going to be changing over time. when we close this, it's going to take some amount of time for the capacitor to be fully charged. And the time that it takes for it to be fully charged is going to depend on how big the resistor is and how big the capacitor is, right? Because we learned that the time that it takes for the capacitor to charge is approximately related to R times C, right? If R is 10 ohms and C is 10 farads, then it's going to take about 100 seconds for this thing to reach about 60% charge, and probably about 500 seconds for it to fully charge up. All right, and you get that by basically just taking R times C. So we know that there's going to be a time over which charges build up on this, right? Okay, so what Maxwell asked was this question. Suppose that I take an Imperium loop and I put it here. And just so that we're clear about what the front and the back of this is, let's erase some pieces of this. So let's do that, and then we'll just continue the red line. Oops. Okay, so that's our path now. And since the current would be flowing in this direction, that's the current, right? Now, instead of using a capital I, though, we're going to use a lowercase I for the current. And I'm going to put a little subscript down here with a C. And we're going to call that I sub C is going to represent conduction current, which is the normal type of current that you're aware of. This is nothing new. And again, this is going to be the conduction current at a moment in time, so it's instantaneous. Right? And so there's our path that we're going to use for Ampere's law. So this is our Imperium loop. Right there. That's our Imperium loop. Okay. So this is what Maxwell was thinking about. He said that if I look at this loop, I can think of a simple surface that would look like this. I'm going to call that surface S1. Okay. And say that if I do integral of b dot dl, and I use the surface S1 and ask the question, how much current passes through S1? The answer is going to be whatever the conduction current in the circuit is at that moment in time. Okay? Okay. This is our current understanding of how this works, right? And we could use this equation. What do we normally use Ampere's law to do?
Calculate the B field.
Find flux.
Not flux, to find what? What did you say, Cam?
The B field.
The B field. So we could use this equation to find what the magnetic field around this loop is, as long as we knew the radius of the loop. And what we'd find is it's basically equal to mu naught times IC divided by 2 pi r, right? That would allow us to find what the magnetic field is around that area where that loop is, and we'd get like a circular kind of magnetic field. Okay, but, and this is something we talked about when we discussed this before, we could do this in a slightly different way. So the other thing that we could do is, we could take a different surface. Imagine taking this surface here and having it be deformed until it looks like this. So use this surface. Now this surface is going to be shaped like a bowl, basically, right? Open on one end, that's the S1 part, and closed on the other end, right? So that's our surface now. We have current coming in here, capacitor plate, and now our surface, so here's the path, and we're creating a surface that basically goes around, like this. Does that make sense? Like a little bowl that you put around the capacitor. But it's open on one side. Does that make sense?
Mm-hmm.
Yep.
Now, if we do that, and we ask the question, how much current flows and passes through the surface, which we call S2, then what we would get is if we use S2 we were to get B dot dl. Sorry, there should be vector symbols above these ones too. I was being kind of lazy when I write that down. When we do the integral of B dot dl, now what we're going to get is 0, because no current flows through S2. Would you all agree?
Yeah.
Because this is a capacitor, right? And capacitors' currents don't actually flow between the plates of a capacitor because it acts as a short in the circuit. Basically, the charge on the plate is only going to build up to a certain point, and then no current will flow. Now, given enough time, what's the conduction current going to be equal to?
Be 0.
Yeah, so as long as we wait long enough, you get the same answer for both of them, right? You get 0. Because eventually there's no current in the circuit at all. Everyone agree with that?
Mm-hmm.
If we let time go to infinity, or in this case to 500 seconds, or whatever we need to so that the capacitor plate is fully charged, then there's no conduction current anymore. And you get 0 for both of these. So it almost feels like the second equation is like partially right. It gives you the right answer after time goes on to infinity. But the first one gives you the right answer pretty much all the time, right? But physical laws don't work like this, right? When we're describing the laws of how things operate, how things interact with each other, how currents, magnetic fields, and electric fields behave, we can't get different answers, right? You can't have one equation that correctly gives you different answers. That's the important part about this, is like, you may be sitting there thinking, well, this is just kind of like a silly, like, why would you even use this surface? If you know you get the right answer when you use this surface over here, why would you ever use the green surface, right? And the reality is, like, again, like, that's how we think in physics and mathematics, is if we write something down and we tell you it's true, then we think it should be true no matter how you think about it, like, no matter how you manipulate it and think about it. Now, of course, it's possible when you're a student, or when I also can make mistakes and I can misapply something, right? But that's a different story. If you correctly understand the idea and you apply it, then you shouldn't get contradictions. That's one of the things about any logical system, right? You can go back to, like, Euclid's geometry. There are no contradictions in Euclid's geometry. There's no postulate or assumption or definition that you can use to prove that the sum of the angles in a right triangle is greater than 180 degrees. There's no way to do that. You're always going to get 180 degrees for the sum of the angles in a triangle in Euclid's geometry, right? And if you somehow found a way to use the same propositions in Euclid and prove that you could get more than 180 degrees in a triangle, it would actually disprove all of Euclid's geometry. You guys know what I mean? Like, if you can prove one contradiction in a mathematical system, you disprove the whole system. So this, in a way, because this is a mathematical system, this would basically disprove all of the things we've learned, unless there's a way to deal with this problem. Unless there's a way to come up with a way to make it so that this part is not true. And that's what displacement current is. Go ahead. What's up?
Yeah, it's like there is a changing E field between the capacitors.
Yeah, exactly. And that's the answer for how we're going to solve this. So we know that between these capacitor plates, that, let me use purple, I guess, that we can draw an electric field. And we know that that electric field is going to look something like this. Now, this electric field creates electric flux. And that electric flux is changing in time, for sure, as it passes through the surface of this. And we're going to use that change in flux to produce something called displacement current. Okay, so this is how we're going to do it. So we know that there is charge piling up on this conductor, right? In fact, we know that the rate at which the charge piles up on the conductor is equivalent to the current flowing in the circuit, right? We know that the conduction current in the circuit is equivalent to the rate at which charge builds up on the capacitor plate, right? And we also know something about the charge on the capacitor plate, right? The charge on the capacitor is equal to the capacitance multiplied by the EMF, right? or times delta V, whatever you want to put, right? So if we plug that into here, oh, and we can go further, right? Because we also know what the capacitance of a parallel plate capacitor is. The capacitance of a parallel plate capacitor. Let me do something so that this doesn't get confusing. Let's use delta V here. We're going to use delta V because we're going to use the E symbol too many times. It's going to get confusing. So the charge on our capacitor then is not C times E. It's going to be C times delta V. So delta V, switch to this one, erase this. There we go. We'll use this, C times delta V. All right. Now, the capacitance of a parallel plate capacitor is something we derived long ago, and it's equal to epsilon naught A over D, where D is the distance between the plates. I don't have a lot of room here, but D is this distance between the plates here. And delta V is equal to the electric field between the plates E. Did I not label this as electric field? So those are electric field lines there in purple, right there, multiplied by D, right? So the two equations that are being used here are capacitance of a parallel plate capacitor is epsilon naught A over D. We derived this in class. And when you have a uniform electric field, the potential difference between the plates is equal to E times D. So, putting all these together, the D's cancel, and we basically just get epsilon naught times E times A, or E times A, what is that equal to? Electric field times area.
That is an electric flux.
Electric flux.
Yeah, electric flux. So look at that. This is such a nice relationship here at the very end. The charge is equal to epsilon naught times the flux. Does this look like any equation we've used before?
Yeah, it looks like Gauss.
Yeah, it is Gauss's law, right? It's Gauss's law, because this is flux. Anyway, not too surprising that by doing this derivation this way, we get an answer that's consistent with Gauss's law. That's really not surprising at all. But nice to see when, we get a result that we can compare back to something we learned before. Anyway, so now what we do is we just take that Q and we plug it in right there for Q, right? Now, it turns out that this is going to be equivalent to the conduction current, but we're gonna call it something else. So if we're doing dq dt here, we're doing ddt of epsilon naught times E. But epsilon naught is just a constant, so we end up getting, oh, that's not, I didn't write that down right. Sorry about that. That should be flux. E times this, yeah, flux. Okay. And then we just get epsilon naught d phi E dt. And what we're going to do is, this happens to be identically equal to the conduction current, but we're going to define this to be displacement current. So displacement current is going to be defined with an I with a D subscript, usually capital D, and it's equal to epsilon naught d phi dt. It happens to be numerically equal to the conduction current, though, because of the way we derived it. So Maxwell came up with this as a way to describe something he called displacement current that he thought of as basically flowing between the plates here. He thought that the displacement current basically flowed from the positive side over to the negative side, and the displacement current basically just came from the fact that the flux was changing. Now, with this, what we can do is we can reformulate Ampere'S law to include displacement current. And it looks like this. And that is our complete version of Ampere's law. So this would be referred to then as the Ampere-Maxwell law. I don't know where that name came from. That's the one your book uses, though. The Ampere-Maxwell law. And as I was saying earlier, you probably came into this class knowing about Maxwell, you heard about electricity, Maxwell's equations. You may not have known what they were, but you'd heard that before, right? Is that true?
Yeah. Yeah.
Yeah, okay. So you may have found it kind of strange that here we are, May 11th, with less than a month left. We have 4 weeks left, basically, right? And we're finally putting his name down. we're finally saying the name Maxwell. I mean, I probably said Maxwell's equations at some point in this class, right? But yeah, I mean, like, it's just this. This is it. It's the displacement current part that leads to this equation, which we're going to see here in a second is going to lead to even bigger things. So, I really find this super fascinating. I don't know if you all find this interesting, but the idea that the thing that Maxwell realized is that when you talk about this integral right here, that you don't have to define the path as to be just the simple, or the boundary of your path, the surface. It doesn't have to be a simple surface. It can be a surface like this. And just with that, like, kind of outside the box thinking, or whatever you want to call it, he was able to figure out that there was kind of an error, something missing in the theory, but that there was a natural solution, which, as you saw, was not very hard for us to derive, right? We didn't need to use anything new. We just used, technically, if you really, really think about it, we could have done this when we first talked about capacitors, right? I mean, I could have just told you that there's this thing we call conduction current, but there's also this thing we call displacement current. I could have just defined it at that time. But I think that your book chooses to do it this way because it's a little bit more dramatic and, I think, historical, to kind of show that this concept of displacement and current didn't really exist prior to Maxwell. So, does anyone have any questions? Let's look at
That
Go ahead.
That mu naught and epsilon looks interesting. Is that going to come into play
This right here?
later? Yeah, that factor.
Yeah, it will.
Mm-hmm.
Okay, so this is your book's pictures of these things, so we can look at these now. I think it always helps to kind of draw, even if it's a bad diagram, I think it helps to see the diagram built from the bottom up, so you understand what's happening. But then once we're done, I think it makes sense to look at this picture. Okay, so yeah, here's their picture of the two different surfaces. Oh, this is something else. So these are the two different pictures. Okay, so the first one is, here's your path, and then there's the bulging surface. And then over here, what's drawn is the magnetic field lines that are produced. Okay, because ultimately what this says, right, what Ampere's law says is that if I have an electric current, there's going to be a magnetic field that circulates around the wire. We spent like a whole chapter looking at that, right? What we now know is if you have a changing electric flux, as you would in between the capacitor plates right here, you're also going to generate a circular magnetic field. That's what this... See, this is the part about this class I think that's ultimately very, very challenging, is you come into this class looking at an equation like this, and you immediately start thinking it's an integral, and you start... okay, like, I don't know what you're thinking. I'm not going to try to pretend that I know what's going through your brains. But for me, at least, when I see this equation, when I first came into studying physics, I just thought it was an integral. And I just assumed, oh, I'm going to be doing integrals. I'm going to be solving this integral, right? Because that's what you do in math class. You just solve integrals, at least in Calc 2 or whatever, right? But the reality is, as you've seen in this class, we don't really ever solve the integral, you know? We just don't. Because really, what this integral says is that if you have a wire, there's going to be a circular magnetic field around it. And really, that little circle tells you everything you need to know. You know, is there's a circular magnetic field around current carrying wires. That's what the equation says. You know, that's what it says. And this tells us that if you have this thing happening, if you have electric flux changing, you're also going to get circular magnetic field lines, because that's what that says. Yeah, it's an integral and there's a line integral associated with it and whatever, but that's not what it says in terms of like words. Is there is a circular magnetic field around an object that has a change in electric flux. That's it. That's what it says. And so in between these plates, you're going to get these circular magnetic field lines on. I wish they would use more colors. The red lines here are the electric field lines, and the blue lines are... they're going this way. The blue lines are the magnetic field lines. Do you all agree with the direction of these lines? I guess I do. Notice there's no negative sign here. So I'm pretty sure what that means is that when the electric flux is increasing, then the magnetic field probably points in the same direction, and when the electric flux is decreasing, the magnetic field points in the opposite direction, right? Right? I mean, it's the reverse of Lenz's law, I think, because here, magnetic field lines are going this way. Sorry, electric field lines are going to the right. So if you point your fingers in that direction and then you wrap your fingers in the direction of the magnetic field, it's pretty consistent. So there we go. So that's displacement current. Anyone have any questions? If not, we're going to kind of summarize Maxwell's equations and talk about how they interrelate with each other. So that's the next thing we want to do. We're going to talk about two different set of Maxwell's equations. We're first going to look just at the full version, and then we're going to look at a simplified version in free space. Okay, so there are four Maxwell's equations. You need four equations plus the Lorentz Force Law to describe all of electricity and magnetism. That's all you need, which is pretty impressive. It's about the same number of equations as what you need in classical mechanics. So the four equations are, they all have names. You have Gauss's law, and there's two forms of Gauss's law. There is the electric form, which is you do a surface integral of E dot dA. This one has to be around a closed path, or a closed surface, because part of what's included here is you have to enclose some charge. Okay, that's Gauss's law for electricity, and there's also Gauss's law for magnetism. And that one states, this is number 2, that if you perform the exact same operation, but instead of using an electric field, you use a magnetic field, because of the fact that you do not have magnetic charges, there's no such thing as a single magnetic charge, which would be an isolated north pole or an isolated south pole, this one's equal to 0. All right. Now, if you really think about what these things represent, because this one describes something that happens when you do an integral of E dot dA, really this equation tells you about the perpendicular component of the electric field. If you think about it, because if you have, for example, some charged particle, draw a surface around it, right? You got some surface. All that this could tell you about, where's a good place on the surface to draw this to show what I mean? Like here? Here. Yeah, here. If I draw a line, electric field line, from here out this way, that's radial, right? It's automatically radial as long as I draw it from here, right? Then there's an angle right here, right? Between the surface and the electric field vector. So if this is the electric field vector, and I come along to my surface right here and I draw my dA vector, it would go this way. So since you have to do E dot dA, you lose all your information about the direction of the electric field that's not perpendicular. Does that make any sense? Like this electric field bit's broken up into components, one that points parallel to dA, which I'm going to call E perpendicular. I know that's kind of backwards, but perpendicular to, basically, this is the component that's perpendicular to the surface. And then we can call this one E parallel. But yeah, you see what I mean? Like, this doesn't tell you anything about what E parallel is equal to. It can tell you what E perpendicular is, though. Because you just lose that information when you do the dot product, right? You eliminate this little piece of the vector here. Okay, so that gives you E perpendicular. Similarly, the equation right here can help you to figure out what the perpendicular component of the magnetic field is. Okay, just kind of summarizing what these things are capable of doing. There's limitations to these equations, that's what I'm trying to say. And that's one of the limitations. Okay, so what are the other two equations? The other two equations are, so Gauss's law. These two, technically, when you combine them together, they're supposed to be able to describe what we call electromagnetostatics. So I'm just going to say that they describe what's called statics. What happens when you have static electric fields, static magnetic fields? These don't change in time, basically, right? There's no derivatives. So these only describe what's happening with static electric fields. And in the case of Gauss's law, it describes static electric fields that are produced by point charges. Okay. The other two equations are Faraday's law and Ampere's law. So Faraday's law, we'll write down first. Faraday's law tells us what happens when we do this equation. I never remember if I'm supposed to put this minus sign on here if we do it this way or not. I think you're still supposed to put the minus sign there. Not entirely sure about this one. I'd have to look back at my notes. I'll look over it in a second, maybe check this. Okay, so this equation describes what happens when you have a changing magnetic flux. It produces electric fields or produces currents, however you want to put it. And because in this case, let's see, does this have to be around a closed path? You can't really have magnetic flux if it's not a closed path, right?
True.
So I think this does have to be around a closed path. So I think this is accurate. Mm-hmm.
And I think the negative is good.
So you can get, yeah, I still think it needs to be there. So you can get, out of this, what you can get is the parallel component of the electric field, right? Because this is E dot dl, so you have some path, and, you know, your path could be like this, and your electric field vector could be coming out this way. These look like they're right angles to each other. I think I just draw the path right here. If I drew my path like this, dl, then dl and E parallel would be parallel to each other. So this one can help you to figure out the parallel component of the electric field. And of course, it also does other things. The other things that we know about, which is that it describes when you have a change in flux, you can get an EMF. I'm also just going to put over here on the other side, I'm going to put a little EMF here to remind you that this describes EMF, but we don't really need that piece. Not for what we're trying to describe now. Okay, and the last piece of this is the Ampere-Maxwell law that we just derived, basically. And that one describes what happens when you do the integral of B dot dl. And now we know that the answer to this is you get mu naught times current enclosed, where this is the conduction current now, plus mu naught epsilon naught times the time derivative of the electric flux. And similar to the previous one, this gives you the parallel component of the magnetic field. Sorry, it looks like some other number, B parallel. So since you can describe perpendicular electric field, perpendicular magnetic field, parallel electric field, parallel magnetic field, you should be able to describe any electric and magnetic field that's produced in any way, whether it's produced by electric charges, magnets, changing magnetic flux, changing electric flux, or current carrying wires. And all of these two at the bottom basically describe dynamics. What happens when the fields or the charges move in time and space. Sometimes this is just referred to as electromagnetism. The combination of these two equations here. You know, in Physics 1A, you learn about statics. It's one of the first things you do. You learn about torques and forces and weights and stuff like that. And then you learn about dynamics for the rest of the course. Things rolling down hills, you know, objects spinning, gyroscopes, all that kind of stuff. And you have equations that describe statics, and you have equations that describe dynamics, right? The statics equations in 1A are sum of all forces is equal to 0, sum of all torques is equal to 0, right? There's two equations. And the dynamics equations are conservation of momentum, conservation of energy, and conservation of angular momentum. F equals ma is in there too, if you want to put it in there. So I think, maybe I'm wrong, but it feels like there's less equations for electricity. Because basically what you need is you need these four equations, and then you also need, we'll call this 4 prime or something like that, I don't know. The Lorentz Force Law. This is never included. That's not never included. Some places include it. The Lorentz Force Law basically tells you the force on particles. So this is, in my opinion, part of the Maxwell equations, because you need it. You can't describe motion if you don't know how forces work, right? So even if you know everything about the vector fields, which these 1, 2, 3, and 4 here, Maxwell's equations, they describe the vector fields, but you also need to know the dynamics that the vector fields place on particles to describe what's going to happen in a system as well. So there you go. Those are Maxwell's equations, all 4 of them. There is pretty clearly a lot of symmetry in these equations, right? Would you all agree?
Mm-hmm.
Yep. There's a lot of symmetry in these equations. The first two is really... Go ahead.
I was wondering, just historically, why are they called Maxwell's equations?
I think it's because he basically did what we're kind of going to do next, which is he took these equations and solved them. Because they represent a set of couple differential equations, if you think about it. Because it's really just the last two that you need to look at. So let's jump right to that. I mean, to answer your question, we might as well just go ahead and go to the next line where we can really kind of pull everything together here. So the next thing to say is, what happens if we take the same equations and we analyze how they work in free space? And by free space, what I mean is no currents, no charges, no magnetic poles. We'll just say magnets. So if we remove currents, charges, and magnets from our system, this is what we get for our equations. I'm not going to keep writing Gauss's law each time. So the first equation is going to become... We really only need to do this for the last two, but I'm going to write the first two as well. First two is going to be that equals 0. Second equation is going to be doesn't change, because even when you remove the magnets, this still is 0. Okay, so there's 1 and 2. 3 and 4 are the ones that change. Actually, 3 doesn't change. 3 is still going to be integral of E dot dl is equal to... Now, if there's no currents, charges, magnets, I'm also going to say there's no wires as well. So no wires. If there's no wires, I can get rid of this n, and it's just going to be negative d phi dt. I think the negative sign is supposed to stay there. I could be wrong, though. And the last equation... Scroll down just a little bit. The last equation is just going to be, what is it, mu naught, epsilon naught, and then d phi e dt. So now, If you totally remove currents, charges, and magnets, these are Maxwell's equations. Okay? And this is the integral form. There's other forms. And what you can do is you can just look at the bottom two, because they describe how electric and magnetic fields interact with each other. And if you read what they actually say, and think about in words what they represent, let's start from the bottom equation right here. Okay, this says that a change in electric flux through a surface produces a magnetic field, right? So I'm gonna simplify that. I'm just gonna say that the fourth equation basically tells us this. If I have a place in space where the electric field is changing in time, okay? What the fourth equation tells me is that this produces a magnetic field, right? That's basically what it says. There's going to be a magnetic field, and it tells you how it's described, and obviously we can use mathematics to figure out what it looks like and all that kind of stuff, but that's not important. Really what it says is just a changing electric field produces a magnetic field, right? Does that make sense to everyone?
Yeah.
But then if we take that and we apply it to the third equation tells us that if I have a changing magnetic field in time, that produces an electric field, right? So the fourth equation basically tells us that a changing magnetic field in time will produce an electric field, right? Now you all know how derivatives work, right? If the electric field, let's say, is equal to something like this, let's say that's our electric field, okay? What this tells us is that if I take a derivative of this, it's going to give me a magnetic field, right? Pretty much. That's pretty much what this says. The derivative of this is going to give me a magnetic field. But we know that if we take the derivative of this, that we're going to get a cosine function, right? And if we take the derivative of that, we're going to get a sine function. And the derivative of that, we'll get a cosine function. And it'll never end, right? So in the special case where you have something like this, and I have a changing electric field, the changing electric field in time is going to lead to a changing magnetic field in time. And a changing magnetic field in time, according to this rule, produces a changing electric field in time. And that process basically just repeats forever. So what that means is, I'm going to take this back to something that's simpler that we did earlier today, right? So the very first thing we did today, we said with induced electric fields that as long as you have a changing magnetic flux, not only do you get an EMF, but you actually get an electric field, right? Now in this problem, and the problem that we did afterwards, we basically just said that our current was increasing at this rate, 100 amps per second. So what that meant was we actually got a uniform electric field, right? Not uniform, but we got an electric field that looked like this. This electric field does not vary with time, right? That means that this electric field, well, I'll just ask the question, is this electric field going to produce a magnetic field?
No,
No. What's the reason why?
No.
because it's constantly changing.
Yeah, it has to be changing. You need to have change to make any of this stuff work. You have to have change. Change makes the universe interesting. It's what physics and chemistry and biology and all the sciences are about, is about exploring change. It's really about what life is about, is exploring like how things operate and change. We don't really care too much about how things behave when they're sitting still. So just given an electric field like this, though, you can take as many derivatives as you want and it'll never disappear, right? The first derivative is a cosine, second derivative is a sine, third derivative is a cosine, fourth derivative is a sine. You don't care about the negative sign, positive sign. You just care that what's happening is that if I have an electric field changing in just the right way, I can produce a magnetic field that changes in time, that produces an electric field that changes in time, that produces a magnetic field that changes in time. And then the process just continues, you know? It just goes right back around to the beginning. And we're going to... So the reason to answer your question from before, Cam, about why are they called Maxwell's equations, is because Maxwell realized that this isn't possible until you add this term. You all see that? This is the term we just added. This wouldn't be true if Ampere's law was true. If Ampere's law was just this piece. It's the additional time derivative that shows up with the flux right here that can also produce magnetic fields that allows you to have this. It's like a feedback loop, right? It's like a feedback loop. Because as soon as you produce the changing magnetic field, that's going to produce an electric field, which if it's changing in time produces a magnetic field. And the process just repeats itself. So Maxwell realized that, and that's why we call these Maxwell's equations, because Maxwell is the person that realized that they were all connected to each other. I don't know if he's the person that realized it, but he's the person that showed that they were connected to each other and then solved the equations. Because you can solve these equations, right? This equation has an E in it, and this equation has an E in it, right? So in a very simplistic way, you could solve the bottom equation for E, plug it in here, and then you could solve for the magnetic field if you want to. That's not really how it works, though, because what happens is that these are coupled equations. They both have derivatives, which means that do you all solve these kind of equations in your, what is it, 220? Do you do coupled differential equations? Where you have multiple differential equations that describe the same system, and you have to solve. Do you all understand the question?
I don't know in 270. I don't know if they do that.
Okay. It's not that hard. I suspect at some point in time you all will probably study something like this, but...
Isn't it just like a system of equations?
Yeah, it's just like a system of equations. And, there's rules about how you do it or whatever, but yeah, with any system of equations, you can come up with a solution, basically, right? I guess what I'm trying to say is, you can solve for E in this equation once you have both equations put together, basically, right? I left off some vector symbols here. So when you do that, it turns out that this is what you get. Or this is one of the solutions. This is a legitimate solution to these equations. This solves Maxwell's equations in free space, and we'll show, we will derive this. We will get to this equation by going through and solving these equations. And Maxwell did that, and what he figured out was that you get, out of solving these equations, what's called a wave equation. And a wave equation is something that if you took 1B, or even sometimes on 1A it gets covered, but it's an equation that describes a traveling wave. And it turns out in this case that the speed of the wave came out of this term right here. It turns out that if you look at these two symbols right here, I think we've done this in this class before, but maybe I'm wrong. If you calculate what this is equal to, if you calculate what 1 over mu naught epsilon naught is equal to, it turns out that this is equal to the speed of light squared. So c represents the speed of light. So not only did Maxwell figure out that you could solve these equations and come up with a solution that might look something like this, he also figured out that the speed at which the wave propagated was given by this expression, technically the square root of this expression right here, which he knew what mu naught was, he knew what epsilon naught was, he could immediately calculate what this quantity was, and it turned out that the answer for how fast the wave moved was the speed of light. And the speed of light was pretty well known in 1850 when he did this. This is on the order of about 1850 to 1855 that he was doing this, which is one of the most tumultuous times in the history of our society, because this is during the Industrial Revolution, when capitals across Europe are being overturned by the people. Monarchies are falling. This is like the beginning of the modern age, you might call it. I mean, it was a really rough time. Industrial Revolution was not a good time. There was a lot of pollution, bad factory jobs, child labor. There's all kinds of negative things that were occurring at this time, but sometimes that's what happens in the history of civilization, is that when major changes are happening, there's a lot of upheaval, right? And during that time, Maxwell figured out that light had something to do with electromagnetism. He didn't really know what it was. He just knew that he figured out the speed of light pops out of these equations, which had to be utterly mind-blowing to him, I would assume. The idea that you just would solve these two equations that describe how electricity and magnetism works, and then you get an answer, and the answer you get, you can actually calculate the speed. You can theoretically predict what the speed of this new wave you found would be, and you find out that it's the speed of light. Now, I wonder if it's either exciting or it's not exciting, because in one sense it's exciting because you figured out that light and electricity and magnetism are all connected together. That is incredibly exciting. But at the same time, maybe he was hoping this was a new kind of wave. You know what I mean? Maybe he was hoping, they knew about sound waves, they knew about light waves. Maybe he was hoping
this was different.
Yeah, like that an electromagnetic wave would be something different. But nowadays we know electromagnetic waves are what light is. That's what light is. It's just a wave of electricity and magnetism. And we can actually see this. I think this is a little bit premature, but I would rather show this to you now than another time because it is relevant. We're about to go on break. I'm just going to show you this real quick, though. We'll put it on the screen during break.
Do you know what he thought about this? Or is it just like...
I mean, I've read his books, but it's been a while, so I'd have to go back and read them again to remember like what feelings he put into it. But I mean, his books are really terse. I mean, it's really just a lot of like pictures of electrical circuits and arrangements of like charges and stuff like that. He does a lot of the same calculations that we did in this class, actually. I mean, if you go back to the early chapters where you're finding the electric field of a line of charge and stuff like that, that's the kind of stuff that's in there. And then just a bunch of differential equations and solutions. It's really hard to read. And I don't think he talks too much about his feelings, if you know what I mean. That's me placing that onto him. I wonder what kind of documents we have now to talk about how he felt about it. I mean, nobody was blogging back then. What do I have to do? What's missing from here? It's called Radiating Charge is what it's called. So I can just find it. No, it's not on here. Am I missing one? Do I have to click the flash button? I hope they didn't just get rid of it. Some of these things probably don't work any. Oh, there it is. Okay, it was Flash. Flash sims are no longer supported in modern browsers.
Wow.
I think it'll still work, though. I don't know what they're talking about. It's just a Java file. At least, whatever. We'll just, Ugh.
The death of Flash.
There's a file you can get to play Flash files on your computer.
Is that this one? Do you know what it's? How do I find it?
Let me see if I can actually send it over. Give me a second.
Yeah, that's fine. I'm gonna go ahead and stop the recording for now, though, and we'll just pick this up next in a second.